So in this video I'm going to record, or we're going to work 4 example problems. The first example problem I want to work with you deals with mole-to-mole conversions. Remember, all stoichiometry problems have to have a mole-to-mole conversion. Alright, so the first one reads, how many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? Well, the first step in solving stoichiometry problems is to get a balanced equation. If you don't remember how to do this, you may want to go back and look at Chapter 8 videos. The second step is to identify our known and unknown. If we go back and read the problem, it's asking us for how many moles of potassium chlorate, so that must be unknown, and 9 moles of oxygen gas, it tells us we have. So we're looking for potassium chlorate in moles, we've got oxygen gas. Third step in solving a stoichiometry problem is to set up our conversions. And when we set up our conversions, we always start off with what we know. And we know that we have 9 moles of oxygen gas. Now, the second thing we need to do is we need to go from moles of oxygen gas to our unknown, which is moles of potassium chlorate. In order to go from moles of one substance to moles of another, we must use our mole ratio. We get our mole ratio from our balanced chemical equation. And our mole ratio is for 3 moles of oxygen atoms, and you must have 2 moles of potassium chlorate. So in order to produce 3 moles of oxygen, you have to have 2 moles of potassium chlorate. We set that up in our box like this. Remember, moles of oxygen has to go on bottom, so it'll cancel. This says for every 3 moles of oxygen produced, we must have 2 moles of potassium chlorate. Moles of oxygen is cancel. 9 times 2 is 18 divided by 3 equals 6 moles of potassium chlorate. Now we need to check our answer and see if that makes sense. Well, if we have 9 moles, that's roughly 3 times the amount of oxygen that you would have in a normal reaction. You would probably have to have about 3 times the amount of potassium chlorate. So just check your answer and see if it makes sense. If it's way too big or way too small, you may want to work your problem again. The next type of stoichiometry problem goes from grams of a substance to grams of another substance. And we know that in order to use or go from grams of a substance to moles of a substance, we have to use the molar mass. Remember, all stoichiometry problems have to have a mole ratio. So, let's start off reading this problem. It says, how many grams of silver will be formed from 12.0 grams of copper? Well, I would give you this equation. Alright, you have copper plus silver nitrate to yield silver and copper nitrate. Copper 2 nitrate. You have a balanced equation. Let's identify our known and unknown. Our unknown must be grams of silver. So we're looking for grams of silver. Don't get confused with grams of silver nitrate. If it were asking for silver nitrate, it would say silver nitrate. We're looking for silver. So we're looking for grams of silver, and we have 12 grams of copper. Okay, so we've identified our known and unknown. Third step in solving a stoichiometry problem is to set up our conversions. Always start with what we know. We know that we have 12 grams of copper. Now, we can't compare grams to grams in stoichiometry. We always have to have a mole ratio. Every stoichiometry problem has to have a mole ratio. So we have to go from grams to moles. And the way we go from grams to moles is by using the molar mass. Remember, the molar mass comes off the periodic table. So we have to go from grams of copper to moles of copper. We look up the molar mass of copper, and it's 63.55 grams of copper per 1 mole. Grams of copper will cancel because it's divided out. Now we're in moles of copper. We've got to go from moles of copper to moles of silver because that's what we're trying to solve for. And in order to go from moles of one substance to moles of another substance, we must use the mole ratio. And the mole ratio is for every 2 grams of silver produced, or for every 2 moles rather of silver produced, we must use 1 mole of copper. Right? So copper goes in the bottom, so it'll cancel. Moles of silver goes in the top. Remember, we get our mole ratio from the balanced chemical equation. Moles of copper cancels. We're now in moles of silver. But the problem asks us for grams of silver, or the mass of the silver. So in order to go from moles to grams, we must again use that molar mass from the periodic table. If you look up the molar mass of silver on the periodic table, it'll be around 107.87 grams of silver per 1 mole. Grams goes on top because, remember, we have to have moles on bottom because it was in the top of the next box, so it will cancel out. Now, we must multiply the top boxes by each of the top boxes and divide by each of the bottom boxes. When you do that, you get a number that's around 40.7. Remember, you need to have the proper number of significant figures. We have 1, 2, 3. That's our least amount of significant figures, so we have to have 1, 2, 3 significant figures in our final answer, and grams of silver. Our next example deals with liquids, liquid stoichiometry, or solution stoichiometry. It says how many grams of copper are required to react with 1.5 liters of a 0.10 molar, that's what the big M stands for, silver nitrate solution. Remember, molar stands for moles per liter. Alright, so let's write a balanced chemical equation. We're using the exact same chemical equation from the previous problem. Then we need to identify our known and unknown. Well, we know that we're looking for grams of copper because it says how many grams. And we have 1.5 liters of a 0.10 molar silver nitrate solution. So that is our known. Okay. We always start off with what we know. And in solution stoichiometry, we always have to have two boxes when dealing with a solution because we have to go from the liquid form to the mole form. Alright, so we always start off what we know. We know we have 1.5 liters of silver nitrate. We have to go from liters of silver nitrate to moles of silver nitrate, and we do that by using this molarity conversion. Remember, molarity is given to you in your problem, and it's 0.10 moles of solution per 1 liter. Liter has to go on the bottom so it can cancel. We're now in moles of silver nitrate. In order to go from moles of silver nitrate to moles of copper, because remember, every stoichiometry problem has to have a mole ratio, we must use that mole ratio. And we get the mole ratio from our balanced chemical equation. We use those coefficients. For every 2 grams of silver nitrate you have, you must also have 1 mole of copper. For every 2 moles of silver nitrate, you must have 1 mole of copper. We set it up just like this. Remember, silver nitrate goes on the bottom so it can cancel. Now we're in moles of copper. The problem asks us for how many grams or the mass of the copper. Remember, if we're going from moles to mass, we have to, or moles to grams, we have to use the molar mass, which we get from the periodic table. And we know that the molar mass of copper from the previous problem is 63.55 grams of copper per 1 mole. Mole again has to go on the bottom, so it'll cancel. If you multiply all of your top boxes together and divide by each of your bottom boxes, you should end up with 4.8 grams of copper. Remember significant figures. We have 2 in the first box, which means we have to have 2 in our final answer, or 2 rather is our least number of significant figures, so we must have 2 in our final answer. The last stoichiometry example deals with a gas. We've talked about solids, we've talked about liquids, now let's talk about gases. It says how many grams of potassium chloride are required to produce 9 liters of oxygen at STP. First thing we need to do is we need to get a balanced chemical equation. Again, that's from a previous problem. Now we need to identify our known and unknown. Well, we're looking for rather 9 grams of potassium chlorate, and we have 9 liters of oxygen gas. Now, we have to go set up our conversion factor. We always start off with what we know in our conversion factor. We know that we have 9 liters of oxygen. Now, in order to go from liters of a gas to moles of a gas, we must use the molar volume. Remember, the molar volume is a definition. There are 22.4 liters per 1 mole. Again, this number is a constant that comes from a previous slide that you need to remember. Liters goes on bottom so it can cancel. Now we've got to go from moles of oxygen to moles of potassium chlorate. Remember, we must always have a mole ratio in each of our stoichiometry problems. We do that, or we get that mole ratio from the balanced chemical equation. For every 3 moles of oxygen that are produced, we must have 2 moles of potassium chlorate. So we can set that up just like this. Moles of oxygen must go on bottom, so it'll cancel. Remember, 3 comes from the balanced chemical equation, 2 comes from the coefficient for potassium chlorate. Alright, moles of oxygen cancels. Now, it asks us for how many grams. If we're going from moles of potassium chlorate to grams of potassium chlorate, we must use the molar mass, and we get the molar mass from the periodic table. You have to add each of these individual elements up. We take potassium's molar mass plus chlorine's molar mass plus 3 times oxygen's molar mass to get this 122.55. Grams goes on top because that's what we're looking for. Moles goes on bottom, so it will cancel. Multiply all of the top boxes, divide by each of the bottom boxes, we end up with 32.8 grams of potassium chlorate. And that's an example of 4 different types of problems you work: moles to moles, grams to moles to grams, um, molarity or solution, dealing with liquids, to moles to grams or whatever. And then the last, or this problem that we just worked, deals with gases to moles to grams. So that's an overview of each of the different types.